Good morning, everyone. It's my pleasure to introduce our speaker today, Professor Alexander Beguet. I'm just going to tell you a few words about me. I'm not going to be very long, actually, but I'm going to be short. Yeah, it's a long list. So Professor Beguet is a full professor at Johannes Kepler University in Austria. And there he also leads the Institute of Software Systems Engineering, And before going back to Austria, he worked in the United States 7 years. And then also he joined as a research fellow at the UCL, University College London. And he's very well known for being an expert in many software engineering topics, systems engineering in general. So like he works on topics like variability management, requirements management, engineering, consistency checking, and so many other topics. So it's really a pleasure to have you here and share the knowledge with everyone. Also, he has published many papers and received many recognitions and awards. So he was IBM Research Faculty Fellow. He also received recognition awards from IEEE and ICM, and many other recognitions and awards. So it's really a big pleasure. I would like to thank you once again for being. In the name of the students, on behalf of the students, to thank you for being able to interact with them, share your experience and knowledge. Thanks again, and I hope everyone enjoyed the talk. Thanks.
Thank you so much. Thanks for the introduction. I hope everybody can hear me from here. I have about an hour to guide you through some of the work we've been doing at the Institute for the past 5 to 10 years, really. So this is trying to cover a very broad part of things. I try to do it very generically, and I try not to go in any theory. But of course, there's a lot of details and theory behind it. So if there's anything in particular that's interesting to you that you'd like to know more about, I'd be excited to answer emails, or even after the talk, of course, answer questions. I can point to the papers. So there are way too many papers around that sort of cover many of the things of the talk. But today, I'd like to really keep it very light and straightforward. First and foremost, I hope my talking speed is all right. Everything cool? If you guys feel like I'm talking too fast, then please do let me know. I can slow it down, but it gets boring maybe rather quickly. The topic for today is, in fact, a very exciting one. It's collaborative software and systems engineering. So to me, this is very exciting because much of software engineering talks about the problem of building large systems and building them as a group, as a team. Yet, when we look at classical software engineering and papers, it's often, not always, but often about one engineer and one problem and something that we can do about this one problem at this one point in time, which of course is useful in the grand scheme. But I'd like to look a little bit beyond that here nonetheless and say, what are the needs of collaborative engineering teams? And that's kind of the focus for today. Thanks for the introduction. I was actually 12 years in the US. I did my PhD at the University of Southern California under Barry Bain. So maybe you guys know the name. Kokomo spiral model to development. Unfortunately died last year. And worked for a number of years at a company called Technology Corporation. You can Google it. It's gone. It no longer exists. It didn't survive me. But it was a small R&D in California, and we did a lot of work with large industrial companies like Boeing, like Northrop Grumman, and so forth. We tried to help them improve their software engineering practices. So I very much enjoyed those 7 years of technology because I was always a bit between academia and industry. And the things that we were doing were being used years in these companies, even if it's on a trial basis. And this is usually in an academic setting, very hard to do, be setting foot into companies to actually listen to engineers, to work with engineers. We like to do a lot in software engineering, and Here, I really had the chance of doing this for quite a number of years. I've moved to Austria in 2008. Before that was at University College London, as you already mentioned that. And ever since, I've been building up a research group there. So Wesley is now part of my group. One of the reasons for coming here is also because, for some reason, a lot of Brazilian people have joined my institute. We're like 5 people now around in my group that are from Brazil. So for some reason, you know, I like to visit Brazil, but Brazilians seem to like to visit Austria. So there's a mutual interest there. And I wanted to sort of explore this also a little bit going forward, maybe during lunch afterwards, to see how we can leverage this even better. Now I have about 20, 25 people or so in various stages, researching all sorts of topics, but you already correctly sort of summarized the main things. Now, one thing that sort of characterizes almost all my work is building complex systems. And that's a word that we all keep saying, right? Because we want to build complex systems. But complex systems can be really complicated, right? There's a company close by that builds steel plants. That's not, you know, some code that runs on a computer and that's what the steel plant is. These are distributed systems, they're so-called cyber physical systems, right? There's hardware, hardware in this case, there's software. And you can go beyond. We're working with a company that builds assembly lines for manufacturing machines. We're working with another company that builds machinery for factories. Actually, this is very much a trademark of the region of Upper Austria that we are part of. We are not so much a manufacturing hub for producing end-user goods. So if you're asking me, what can you buy that has been produced in Upper Austria, you probably wouldn't buy much. Haribo sweets, maybe. Haribo, you guys know, like the little gold bears that they're actually in lids. But there's little being made that you would buy. But a lot of the machinery that factories around the world want to buy to build their factories are actually coming out of that region. Whether it's bending machine, whether it's plastic injection machine. I mean, all of you played Lego, right? Not a single Lego block comes from Upper Austria, but some of the main machines that are being used to extrude plastics that are being used by Lego are coming from Upper Austria. And these companies are our industrial partners. And this brings us to a very unique position where we are in this. So it's not that we're trying to help Lego build nicer Lego blocks. But we're trying to help a manufacturer of machinery, which is a complex system, build that complex system, which will eventually end up in an even more complex system, like a factory. That is somehow a network of possibly multiple factories. I mean, hardly a factory works in isolation these days. And that creates this whole idea of cyber physical systems and what to do with that. So when I worked with when I went to Linz, I went to Linz mostly with my software engineering perspective. But when I arrived in Linz, a bunch of people kept knocking on my doors who were not software engineers. So mechatronics departments, very popular. And you know, electrical engineering, mechanical engineering, hydraulics, aerodynamics, you know, all these kind of beautiful things that we have no idea about. I don't have an idea about. Maybe that's different for you guys. And these guys kind of knocked on my door and said, you know, we're building these wonderful systems, bridges and sky rises and steel plants, but we don't know what to do with software. At the same time, it's almost arrogant from us software engineers to say, if you want to understand my software, here's my Java code, just read my code, right? That's not software. Sure, that's what the computer interprets at the end of the day, but that is not what a human should be consuming. Even though we'd like to think that all the software engineers is, you know, looking at the code of somebody else's person, if it's nice and documented and has beautiful names and there's method names and variable names, we feel like that's already accomplished a lot. In reality, there are a lot of people who could not possibly read your code, not because they're lazy, not because the code is too complicated, but because they've never studied computer science. Yet they are working on systems where computer science plays a very integral part. So we can look at this thing. So this was a case study with a Belgian company, Connect Automation. They built conveyor belts. Conveyor belts are these moving things where you put something on top and it sort of moves along, and then maybe robots do things with it while it's moving along. And then they build these robotics, and I think they buy the robot arms that interact with the conveyor belt in some ways. And they basically came to us with a story, and that story keeps repeating. It's always in variation, always the same story. So we had our engineers sit down, they built the system, it's working wonderfully, and then something changes and everything breaks. And this something changes and everything breaks is the recurring theme that happens. So how does engineering work? I'm very simplifying it, of course. You guys know that here. But there are people involved, not necessarily computer science people. I mean, you know, there's this person here doing some use case description. If they happen to be using UML, whatever they might be using, right? There are other people who might use design languages, for example, again, UML. But in our domain, there are other tools being used. You know, Microsoft Excel is a very commonly used engineering tool, as much as we don't like to think of it that way, but it's being used for lots of calculations. In this case, by the way, we're building a robotic arm, in case you're wondering. And here is a little Excel sheet that computes how long the arm has to be for me able to reach, for example, this cup. And you know, the arm may not be able to stretch completely. It may have to be bent, so there are angles involved. And based on the distance of the cup and based on the angles that are possible, I have to design the arms in a certain way. This is trivial. This is high school math. I think all of you can understand this if I explain it to you. All right? It can get more complicated than that, of course, but that's not important for my talk. The important thing is this information moves around. It's not that this person keeps it a secret what the length of the arm is. This is, of course, information needed by other people. For example, this lady doing the cat drawing needs to use the information that was given here, right? And once you understand what the arm length is, you know, maybe there are different designs, different lengths that you can purchase. Maybe you don't get a 17.7 millimeter arm. Maybe you have to get the next bigger one, the, you know, round it up to the next 50 or something like that. And that's okay. Then this is what this lady will decide. She will design this thing. And of course, that information is then also being further propagated to get other people, at some point, even to software engineers. Right? Because how can we possibly write software that controls a robotic arm if we have no idea what the dimensions or the angles are that we can use or exploit? So this communication is what interests me. What did they have to talk to one another? And this is where it gets very blurry. Anyone uses a tool that you use for communication? Anyone transcribes your communication? Any engineers you're working with keep writing down everything they mention to everyone else about anything relevant to the product? You can go on a coffee over there afterwards. Anyone taking a notepad along and transcribing that? You should not, right? Is that important for engineering? Maybe it is, because at the end of the day, it's not one person, two persons, 3 or 4, but hundreds. Can be thousands of people. And what these lines are supposed to indicate are lines of communication that we talk to one another in some ways. And this is the knowledge, the combined knowledge of a complex cyber-physical system. All the things that the individual people are doing, but also all the things they communicate to one another as part of the engineering process. So, obviously we have mechanics, computation, electrical, requirements, design, simulation, planning, programming, whatever it is. And now you can also tell why I really like to work with the mechatronics department. This is a little side note. Whenever I work with just computer scientists, when I start about, UML, they're like, no, please stop, we're real software engineers, don't bother us with UML. If you work with mechatronics engineer, you never have to argue why you need models. They live models, they work models. They literally build and design models all day long. They use them as analysis platform, they use them for simulation, they use them for synthesis, for generation. And this is actually very beautiful because a lot of the things that we like to do as part of our work motivates what they actually live. And at some point, even software engineering has to find its way of interacting with that world. This is what I'm trying to facilitate. But my point is not that. My point is a different one. What information here is explicit? It's the information inside the tools. Anything I put in Excel in saved is at least saved. If I'm deleting it, it's there. I may still have to find it, right? All the information that moved around, that somehow made it from that tool to this one, from this one to this one, is not explicit. And this is what happens as time goes by. Basically, all we have left are these islands of knowledge and nothing that connects them. And this introduces my first term of my lectures. You saw it in the title. I said I will talk about collaborative engineering. Yes. And I said I will talk about traceability and consistency. This is what for me is traceability. Being able to connect knowledge, especially if that knowledge comes from different tools, from different people, from different domains, but it doesn't even have to come from different tools. It can even be within the domain. If I don't have traceability, how can you maintain this information? Do you think when Boeing, so I worked for 3 years for Boeing, the guys who build the airplanes. When a new airplane comes about, do you guys think they just throw away everything they've ever done about airplanes and just build a new airplane, and then the next airplane is again everything's thrown away? Well, they're gonna build on the existing knowledge. Obviously, they build on the existing knowledge as much as they can. It's sometimes a problem, as you see with the Dreamliner, that building on the existing knowledge can also be dangerous, but that's not the point. The point is, if that is the knowledge that exists, you cannot build on it. So, obviously, people are the ones who start this process, maybe sitting around the table, maybe writing emails. It's obviously people going their separate ways at some point, using all sorts of tools, and maybe at some point trying to make sense of what they're doing. And this brings us to the next part or the next term of my talk, which is consistency. I've spent a lot of time talking about consistency in my research. But the problem with consistency is that within a tool, it's trivial, like making sure that my requirements document is internally consistent means make sure I've used the right naming convention and I always name the things the same way. And I just called that trivial. That's really hard. But that is trivial in comparison with the fact, what about consistency between these tools? What if, we meet, design a system, go separate ways, build something, and some of us have misunderstandings. So I have this all the time. We start creating inconsistencies with different tools, across different tools. Maybe I communicated the length of the arm incorrectly. Now you guys are computing with wrong parameters. Right? Happens. You guys probably know wonderful examples. I love the one from NASA and Lockheed Martin with the spacecraft that was supposed to go to Mars, where one, yes, notice the case, two engineering teams, one from NASA, one from Lockheed Martin, and they exchanged information, but they forgot to exchange the units of measurement they're using. I mean, are we talking complicated computer science here? This is the most trivial kind of thing that is about human communication, right? And this is just one example of an infinite number of things that can go wrong, right? So it's this exchange that has to be somewhat meaningful. So coming back to my example with the robotic arm and the conveyor belt, I mentioned to you beforehand that company says everything is going well. All the engineers know what to do. The first person knows the design. he or she knows how to send information to the second person. They somehow figured out how information needs to flow. Then something changes. It changes that. Right? For example, a safety engineer may discover that you can pinch your fingers in a conveyor belt. Well, that's bad too. What do you have to do? Well, they need to think of solutions. Maybe they might decide, well, if you can pinch your fingers, we need to add some version of a cutoff switch where you can emergency shut off this thing, or maybe recognize a certain delay of movement in the motor so the conveyor can shut off, which is good because you don't want to have your fingers ripped off, right? So maybe this person will talk to that person. That person, I'm not sure if you can recognize this. This is an E-plan drawing. E-plan is for electrical modeling, electrical drawings, very commonly used for an industrial standard. In the electrical world, this is like the EML. Okay? So the guys, they model things like a motor, and these are physical wires with electricity flowing between them. This is maybe a switch they can turn on and off. And when a cutoff needs to be introduced, the electric needs to change. Okay, so be it. So this person now changed the electric. But here's this other person who is working on the code of the system. And the person who works on the code is, our software is interacting with the hardware. If the hardware changes, our software is no longer interacting the right way with the hardware, right? It cannot possibly work. So whatever you change on the electric somehow needs to be reflected on the software. Now we can be mean, you can say, here's my E-plan drawing and send it to the software engineers. I'm sure you figured it out. This is like you sending the source code to an electrical engineer and asking them to figure it out. They will not work. So they need to somehow, again, work together as a team to understand what this change implies and what it implies for this person and vice versa. And this is the notion of change and how it propagates. And the problem that all of you are surely aware of is these changes are not exceptions, but they're the norm. They happen all the time. And this is exactly where engineering has so many points of failures, mostly starting with changes that people are not fully understanding. In most cases, that's what it is. All right, let's fast forward here a bit. This is a fairly huge area. We can talk for days about this and all the problems that and I don't have the solution for you right now. But we're working on something called the design space, where we're trying to support an engineering team. And you might ask yourself, well, this must be grandiose. Of course, it has been a large project. There have been dozens of people involved over the last 5-6 years to build what I'm going to show you the next half an hour or so. But the thing really is, the principles of the design space is very trivial, because the only way on how we can ever provide meaningful traceability, like just connecting all these islands, consistency, change propagation, error checking, whatever it may be, is if engineering knowledge comes together. It would never work if each tool is separate, obviously. So the design space is simply a platform for representing engineering knowledge. You can put anything in a design space. Think of it as a, as a cloud, as a place where you can dump your data. But this is the funny thing about clouds. People think that clouds are wonderful because you can dump all your data there. But the thing is, what happens to this engineering data if you dump it in the cloud? It is still islands of knowledge, happen to be sitting in another different place. So that doesn't do anything. So the design space is providing not just a place where you can dump data, but you can do it in a way that the data is well-defined, but also extensible with traceability and consistency information. So you can automatically do things with that information in a meaningful way. So in a most simplistic way, it simply means that each engineering team, each engineer is forwarding whatever changes happen to the design space. And in the design space are linking, which is traceability, sharing, like, when you have GitHub, when you want to exchange and share knowledge, want to get something one engineer to another one, or consistency services, or you can add more services if you like to. Yesterday we talked about bad smells. So you can do a bad smell detector there if you wanted to do that. And because of all the information being in the design space, it becomes fairly simplistic to provide these services. But here's a catch. We have platforms, clouds that already have data storage for engineering artifacts. GitHub, I mentioned it before. I could just use GitHub and throw all my data in there. But there are two problems with that. Problem number one is, how often do you guys commit something to GitHub when you work with it? Every 2 minutes, every 2 hours, every 2 days, every 2 weeks, 2 months. Right, I mean, it's probably not 2 minutes. So whatever you put into GitHub takes a while usually. So this is rather a slow process of getting information alive. But that's not the problem. It's part of the problem. The problem for me is, can you actually understand what changed in GitHub? When you think about it, think of source code. All of you are computer scientists, I think, so source code is the most comfortable. Think about, you make a change to some code, you commit it to GitHub, you change the code some more, commit it again to GitHub. What is GitHub telling you about the change? What is the information you get from GitHub? Well, what does it know that changed? It will tell you which lines of code. I would not even say lines of code. It tells you which lines of text changed. GitHub has no idea of your code. Almost. They have some little things and automations in place that does some minuscule analysis, but for the most part, GitHub doesn't understand that data. That's problem number one. And GitHub doesn't understand the change. It understands that lines 17 to 19 were removed. It understands that lines 25 to 27, something was added. If it has a little bit of clone detection, maybe it recognizes a movement, but sometimes not even that. This is not change. Diffing, so a diff mechanism doesn't actually tell you what changed. If I rename a method and I change a few things inside that method, GitHub might actually think that you deleted the old method and recreated a new one for the class. You might leave, we've done work, one of my PhD students has done work where she recreated the history of GitHub, not the way GitHub sees it, but using refactoring as a basis, trying to understand what really happened to the code in terms of changes. Because if you rename a file and move that file to another folder, GitHub thinks gone. And if I ask GitHub for the history of that file, it will say, well, it's brand new. I cannot tell you anything about it. It just appeared. In reality, it was there all along. It has a long history, but under a different name, in a different context that GitHub no longer recognizes. So this is not change. Design space is change driven. The most atomic thing in a design space is a change. I added a method. I renamed the class. And that's incredibly important for anything that we do. Yesterday's talk with the bad smell detection, you had this discussion about needing refactoring as the basis to make some sense. Why? Because refactoring gives you meaningful changes. Diff would have been entirely useless to you. And that's exactly the same idea with design space. You need meaningful change chart. So that's the basis of the design space, and then it can provide meaningful analysis on top. So all of it sounds nice and easy. Oh, by the way, I missed one part. All of this is incremental. So you make changes, all this information goes live into the design space. And some people might like, oh, wait, if I do something, it will immediately break something and all sorts of other people are upset. That's not the case. I will talk to you about this later. Let me give you a little example, and I have some short movies. This is still about 25 minutes.
Yeah.
Okay, good. For example, you want to connect knowledge here. For example, you want to take this one tool where you have these use cases and you want to connect it with that tool that has this robotic arm. These robotic tools, by the way, are pretty smart. It's not that they have notions of lines and geometry only, but they usually also have notions of components and parts. So you can actually identify parts as a whole. But let's say you want to make sure that for every part there is a use case. Why would you want a piece of hardware in your system if you don't have a use case for using that part? In this case, trivial. But remember, steel plant, not that trivial, right? So this connection, how do you build this connection? This is UML modeling tool, I don't know, Papyrus, Paradigm, whatever you want to use for UML modeling. This is, I think this is PUC-Rio, something, CAD modeling. They don't know each other. They're engineers, maybe met at a conference, but they're not really talking to one another. There is no import-export mechanism between these two worlds. It's basically, there's nothing there. So what could we do? I mean, what could we do? There's this whole software engineering community that writes papers about traceability and how to do automations. This is traceability. So how do we do the most basic thing, meaning adding a trace, a link between one tool and another one? And the answer is you can't. The best you can do is write a comment somewhere, open maybe a Word document, Excel. People like to use Excel for traceability because now you can use the columns and the rows to identify the elements here and the elements there, and you can make little X's in there. Works beautifully until someone is doing what? Changes something. We just said beforehand, changes the root of evil. It will kill every software engineering project right there, anything that we do. So that's the plan work. In the design space, all the information goes from the tools to the design space. And let me start these videos, and I hope they're coming across okay in the YouTube world. If not, I'm sorry. But, let me pause this for a moment. Shouldn't have started quickly. On the right is IntelliJ. All of you know IntelliJ, Java programming. On the left is a simple requirements tool that has two requirements. A robot has to be able to put down an object, and a robot needs to be able to pick up an object. It's really complicated. On the right-hand side is some code that actually looks a bit more complicated about what it means to grab an object, and it requires some motions of the gripper, the close, for example. And we want to create traceability between these two now. We are working with a company, for example, with Bosch, where they do this. Engineers do protocol and do monitor requirements to code traceability. So this is not something that maybe somebody would sometime want to do. This is done by engineers on a daily basis. They have to do this because of certification. They build parts for a car. The car is not allowed to drive unless the process is certified. So they need to somehow get these connections going. And in this case, it's fairly straightforward. In this case, in a design space, so I'm showing you the solution. We can go back how this might work a bit later. In the design space now, I have the requirements represented. I have the code represented, not as text lines, because it's meaningless, but the code as meaningful artifacts, classes, methods, parameters, statements. And I can now go about and actually in the design space, create a traceability link type. I can say I want to connect a requirements type. So the design space is a typed environment. Everything has types for obvious good reasons. And on the left-hand side is methods. So I want to select that I want to be able to create links between requirements and methods. And then I can select where the elements align, and it will automatically generate this traceability table, where I can now pause this for a moment, where I can now, as a human, put those little X's in there that I mentioned beforehand, right? I can, for example, say that picking up an object is implemented in the base run. It's not implemented in gripper open. Makes sense to open the gripper, probably doesn't make sense for picking up an object which will close the gripper. And you'll also notice a few other things here. This is not just a place where I can create links right now. There's something else happening. I mentioned beforehand that once you work with a design space and you have this change tracking world enabled, you can have these services that listen in and provide assistance. So doing this automatic propagation of changes directly to design space is not about big brother listening. It's about services providing services to humans. In this case, there's a service in the background that provides the engineer with assistance that, oh, you said that this should not be traced to that and that should be traced to it. I don't think that should be traced. It might even contradict what you said. This is what the red color here means. So there's a service that provides a warning that says something you're doing right now doesn't seem to make sense. And you might ask yourself, how the heck can a service know what makes sense or not make sense for traceability? And then you can read, I can point you to 100 papers about how to do automatic traceability. Yes, there are ideas. For example, you can use calling relationship. If a method implements a requirement and that method calls another method, I can tell you right now, it's very likely that that other method also implements the requirement because they call another for a good reason. So this service uses that knowledge. In fact, this is a whole PhD thesis, almost 2 PhD theses, just to make this happen, which looks so simple right now. Okay. In context of the design space, this is trivial now, but of course, the theory behind is what we do in software engineering. That's why we do software engineering research, to actually then provide an effective mechanism to utilize these ideas. For the fun of it, I can finish this one. So there is a problem that picking up an object, the automatic service said it should relate to a method called release object. And any human here in the room will say picking up an object is probably not related to releasing an object. So why would this service that a PhD student did recommend that this is in fact a trace and now contradicts with what the other human said? Very simple, because somebody made a programming error, a method call that's wrong. And this is something you can do in the design space as well, since everything is live. Let me finish running through. You might discover that somebody did something wrong. Instead of opening, closing the open as a method call, and the inconsistency just went away automatically. This is also the notion of change tracking that I'm talking about. So by being live, being instant, we can actually monitor what people are doing and provide meaningful results. All right. So far, so good. Did I not lose you yet? Cool. We can now go through many scenarios, and I will go through some in more detail, maybe others not. Error detection, for example. If you are Bosch, that company, you might be interested in making sure that all the requirements have been traced, or that there isn't any code that has not been traced to any requirement, because they need to do this for certification, right? And so they can now use the information that we already have. We have the code, we have the requirement, we now have traceability, and we could now actually in the design space come up with a consistency rule. This is what this thing is out there doing. We use OCL, the object constraint language. It's commonly used to express a consistency constraint. I'm not going to tell you exactly what it means, it takes too much time, but basically all it says is for any given method, we expect at least one requirement to be tracing. And you can already look at the picture here on the bottom right and see, well, this doesn't quite look like we're done. Like we see there is this point class that does not trace. So here in IntelliJ, we can now open up this point class. Here it is. You can hover over this code. You see there's this wiggly line. You guys know this wiggly line in IntelliJ, and usually it's bad news. It just tells you that something is wrong. And this wiggly line, when you hover over it, it says that you have forgotten to trace that particular class to a requirement. And now you might ask yourself, hold on, how does IntelliJ know about the requirements? but it knows it about from the design space. So this is the second purpose of why we link tools to the design space. One is to provide information to the design space about what the engineer is doing. And on the other hand, to retrieve information about what the design space has to say about it. For example, if there's an inconsistency generated or a trace recommendation, you might have asked yourself how that happened. It's basically a reverse change propagation that's coming from the cloud, from the design space back to the tool. And in this case, this was a student's work. The student then highlighted inconsistencies in context of IntelliJ in a way that was meaningful for IntelliJ. So imagine back to Van Hoecke automation. Remember this engineer who works with the electrical engineer and they have to deal with a change? This is maybe the point where they start realizing something is wrong. Because now imagine there's the electrical drawing in the design space, there is the code in the design space, both of them happily working, but they start violating consistency constraints. And that's exactly what we did with Van Hoecke. We showed them how to write consistency rules so that you can automatically detect inconsistencies between electrical drawings and source code. How that works, I can point you to a paper. Okay? You might ask yourself, that sounds silly. And the thing really is, it depends on the domain. It depends on the application. You can create situations where you can come up with rules, depending on what discipline you use. And a company can make its own rule when it comes to engineering. So in this case, then the information is projected back to the engineers. And now will be the point where these two engineers are aware that something's wrong. We haven't helped them fix the problem yet. But the biggest issue with change propagation is not knowing that there's a problem. If people knew there was something wrong with what they just did, they probably would fix it. But usually they think they're done, and that's exactly what the problem is. So we can create a situation where this is. But of course, this is yet another part of our work at the Institute. Actually, one of our PhD students from Brazil, Luciana Machisan, is doing automatic repair generation. Because you might ask yourself, so okay, cool, now I know that my electrical drawing is inconsistent with my source code. What do I need to do to change the source code to make it consistent with the electric? It's not an obvious thing. And what Luciano in this case is doing is automatically generating repair choices. It can tell you which things in the source code you could change to affect the consistency. Here are a million lines of code, but these 5 lines have a chance of fixing it. Maybe you still need to figure out what to do there yourself, but hey, that's useful. And these are exactly where a lot of our research is coming in. So as you can tell, the design space itself is actually not our research environment. Our research environment is what we can now do with the design space. For example, repairing an inconsistency from an electrical model to some source code, which is an amazingly complex problem. Oh, this is actually directly from the Van Hoecke automation. I can skip it. Here's yes, I cannot start it. Sorry, doesn't matter. This is the E-plan tool I was mentioning. This is the source code. The link doesn't seem to work right now. I could show you how to automatically do the consistency checking between the E-plan and code. But I'm sure you believe me. If you don't believe me, I'll send you a paper. I'm happy to do it. Propagate changes. I mentioned Luciano's work, where the propagating of changes is more like an identification of other places you should change or consider changes, but not necessarily knowing how exactly to change. We had that also in the talk yesterday. There was a lot of parallels to yesterday's talk by Anna, where we're trying to point to places, point out possible side effects. In fact, his work also talks about side effects in some of the other PhD students, because when you repair something, it might break something else that now you also need to repair. So this is an exploration process. This here is a trivialistic version of a repair that is so trivial that I was actually initially surprised when we should even do it, but it turns out to be, even that is already quite useful in industry. When we think of an electrical model in source code and repairing it, you're thinking very complicated. Like, what is an A-plan change implying in source code, it doesn't seem like a trivial answer. It seems like it's a complicated reasoning process. In a lot of cases, it's not complicated. In a lot of cases, it's actually trivial how to propagate information from one tool to another one. In a lot of cases, it's actually information duplicated. And in the science space, you can handle that just fine too. I can show you that maybe in the next example, run that. Still have a few minutes. On the right-hand side, you see a different tool work that's called SolidWorks, commonly used. I don't know whether anyone knows SolidWorks. On the left-hand side, you see, let me pause this, sorry, it's going too quick. On the left-hand side, you see a tool that probably has never seen before. This is called TechCalc. It's built in Linz by a competence center called the Linz Center for Mechatronics. And it's actually a pretty cool tool if you're a mechatronics person. Basically, what they do is they try to solve equations of, simple to complicated mathematical equations, but so that you can choose from what dimension you want to calculate. And the easy way of explaining it is, all of you probably in school calculated circles. You have a radius of a circle, and based on the radius of the circle, all your children or yourself probably can tell you what the area of the circle is. But you can also do it the other way around. You can say, what if I have the area of a circle? It can compute what the radius is. So that's exactly what this tool is doing. It understands all these equations, but it doesn't care from which direction you want to compute. You give it all the values that you want to give, and it will try to compute all the other values that it can possibly compute from it. Okay, you don't need to understand any more than this. You can imagine why engineers would love this. Okay, what does that have to do with this? Very easy. This is my robotic system. And this is my modeling of the robotic system, and it's doing things like bending. When you have a robot and you put weight on it, it will bend a bit down, metal will bend. And that is being calculated. Don't ask me how, I'm not that good, right? And these here, I think, are the movement calculations. Like when you grab an object and move it around, then this object makes a certain movement in space. This is supposed to be this way. So you can see this is a bit more complicated than what other ones do. We don't care about any of this complication, but what we care about is how they affect one another. For example, somewhere along the line, somewhere here, you specify where the locations are of the object you care to pick up. Based on this, a certain distance is calculated between me and the object that needs to be picked up. And somewhere it specifies the material of the robotic arm being used and how much it bends, and don't ask me what. And somewhere at the end, it will compute with the length of the beam necessary to achieve this. So it considers now the same arm length calculation that we've shown before with Excel, but a little bit more technical. Okay. So if I now change the location here on the left, nothing should happen on the right because they are separate tools. But of course, we build a tool that influences one another, so we can actually link this in the design space. So if you start modifying the one tool, it will start automatically updating the other tool. So the SolidWorks just redrew itself because the arm length changed, because it was changed in another tool. And in this demo, I don't want to show you the whole version. We even started from the requirements. Like in the requirement, it specified, I think, the distance. It will then translate it over to TechCalc, which is then translated over to SolidWorks. So you can now multiple hop change propagation of a very trivial kind, simply replication of values. And we weren't even quite sure how the community would react to that because this is so trivial. This is not scientific. Copying values from one place to another place, what's a scientific contribution? There is none. But the fact that you can use a mechanism like the science space to so simply implement this is the contribution. And we were actually quite thrilled. Certain models a couple of weeks ago, we got the best paper award, for example. This is one of the many applications that we are doing with industry. And you can tell from my examples that the way we work is very interactive in one sense that we do things on our own, but we also like to work with industry and try to really see how what we're doing affects them in some ways. All right, fast forward. Almost no time anymore. You might like this one here. This is kind of cute. Imagine you're using Visio. Visio is a drawing tool. In Visio, you can draw shapes, and you can draw a state chart diagram in Visio. And Visio doesn't care what this thing is. You can connect a final state and make an error to a starting state, which makes no sense whatsoever. But Visio is very happy to do this for you. Once you connect Visio to the design space, you can now use the consistency mechanism of design space to add meaning and rules. For example, we just added a shape here on the left, and it made it red. This is not Visio doing. This is again an inconsistency that's being propagated back. Why was it red? Because it didn't have a name. Visio wouldn't care. I added a final state. It actually has a name, but it is a non-reached final state. You cannot have a final state if it isn't reached. So you can do analysis for that. I can reach it, and that goes away. Actually, another one comes about because you cannot directly go from initial state to a final state. That's also illegal. In other words, you can come up even with domain-specific rules, engineering rules, how to govern yourself, and support engineers that way. Why do you see this twice left and right? You might wonder yourself. Because this is another little feature of the design space where you can share engineering knowledge. This is in fact Visio running twice on different computers with different engineers who chose to work together. And let me remind you, the design space is a change tracking mechanism. A change that's being made here on the left-hand side will be instantly propagated to the design space, and it can be as quickly propagated to another tool. So you can now create a Google Doc-like experience with Visio. You can make a Google Doc-like experience with the UML modeling tool if you want to. It's simply propagating changes around more, and this is another purpose of these adapters. So you can actually do pair modeling with, in this case, domain-specific constraint support. All right? So all this gives you hopefully a bit of an idea. I don't know. Bore you a bit too much. Maybe as a very last example, I still have a few minutes. I can give you this one because this one is again motivated from a real use case. Wesley, sorry, noting we just had a paper accepted at ICSI saved for this work here. This is again working with Belgian Competence Center, and they are working with a company whose name we don't know. We cannot know, but we're not supposed to know. I cannot tell you. They build big machinery being used in the agriculture thing. So there's big machines driving around in fields. That's all I can tell you. And what they do is they build systems of systems, and the components of those systems have well-defined interfaces. Super, we like that, right? And these are these components. This is a little part of it. They actually use Visio for modeling them. So this was like a coincidence for us. And they would, for example, describe these interface declarations somewhere in Visio. And then these interfaces will be implemented also in code, but in different code parts. Because if you build now a system of systems, and you have an interface between two of those subsystems, then you need to have one GitHub project, perhaps, where the same interface declaration exists, and another one where the same exists, so you can communicate correctly to one another. So now you have replication going on the code level that somehow has to match the specification on the model level. It's a beautiful example of what we like to do. The reason why I'm showing this is the very last example, and then I don't bore you anymore, is because we can also interact with cloud platforms, in this case with GitHub. So you see somewhere on the right changing the Visio.
Yeah.
I hear myself back, maybe. You can see it just turned red because the interface here is no longer consistent with that. I can now go to GitHub. Nobody would edit in GitHub directly, but you could. You can also just check it out, change something in GitHub. adding the same thing, choose to commit this in GitHub again, and this thing over there should be turning blue again in a moment. This is the nice thing about recordings, they will always do exactly that instead of live demos. And yes, here it is. So even cloud platforms like GitHub or Azure, you're working with those, can be integrated just as elegantly in this case. So to summarize, what I meant to show today was maybe an invitation. The design space is something we built over the last years, not because we think it's the answer, but because it's an environment where we can experiment about when the answer comes about that we want to have. And maybe it's never called design space. Maybe some company comes up with some ways of getting engineering knowledge properly together. But we still need to solve very basic problems, like how to automatically trace information, how to automatically find inconsistencies, what kind of inconsistencies are important, how to repair things. So the design space is a platform where we can play out that future at the moment for us, using real examples from industrial context, but also making up our own, perhaps. And we are sort of at the point where we now actually have people experiment with it, where we can actually do meaningful examples. Again, this is not a product. We are not a company. I'm not selling you licenses for a product. I cannot possibly do it. This is simply a research prototype that has over years now matured to a level where I feel people can start using it for experimental purposes if they have interesting questions. For example, trying to explore that smell repair with a multi-user context, where it would take an amazing amount of time to figure out how can I make two IntelliJs now work together. Already done. All you have to worry about is now how can I build a service that provides this added piece of knowledge. And this is what I like to sort of offer a bit as part of this talk, to see if there are even interesting ways of connecting with this. I didn't present a bunch of slides because I could talk for hours about this. You can tell I'm excited. Yesterday's talk had a lot of emphasis on variability, also research being around. And that's exactly one of the things that we get very, very excited about. I guess I showed one slide, but I'm not going to talk much about it. Guess what happens when you have variability? You often copy and duplicate information from one product to another one. My first steel plant and my second steel plant, and then I'm talking about a product line. But these are now variations of the same products. I now have two E-plan models for customer one and for customer two. I have two source code variations. And now it gets very excited to start thinking about what that means in terms of collaborative engineering. What if I, just bear with me for a moment, what if I want to take, going back to the robot, I want to take this yellow gripper, whatever the yellow gripper is doing, it's yellow. Maybe it's not just color, maybe it is a soft gripper that can handle eggs. Let's just say it's doing this. And I want to take this yellow gripper, but I want to take something from over there. This yellow gripper is not just a piece of hardware. There's also some piece of software, some piece of electric attached to it, some drawing in the CAD drawing tool, and so forth. So I'm visioning sort of a world where you can literally sort of take features out of the design space and not just the code variations, but attach to traceability all the other things as well. So you can actually track these things out. And it's actually an amazing research challenge how I would now take this feature and plug it into another product. Because I'm not just plugging in code, I'm plugging in a fragment of a drawing, I'm plugging in a fragment of a computation. What does that mean, right? It's an extremely exciting research problem. And now I'm really stopping. So we have a few minutes of questions if you like to ask.
Questions?
I have a question, actually, well, two questions. First of all, I understand that you are handling a very relevant topic, which is the communication within multidisciplinary engineering teams also. We have, for instance, mechanical, electrical, software engineers working together. And I see that design space kind of represents a solution option for communicating changes between these. We did a project once focusing on causal analysis within this specific context of multidisciplinary engineering team. So it was actually done with Stefan also and the Kristen Doppler lab. And the main issue that we identified with the causal analysis was exactly the communication between the different disciplines. And one of the recommendations for solution options to handle this problem was exactly identifying the common concepts and linking them so semantically, so that we could propagate the changes and communicate the different parts. So as I see, the design space represents a solution option for this. It could have been used in this context to implement this identified solution proposal. Or did I get it wrong?
The design space is kind of like a hammer in this regard, and you have choices how you could deal with this problem. Stefan Biffel kind of likes to think of transformation. Like he has this automation ML focus that a bunch of his Sevilla lab is doing. And he likes to think that you can take things and transform it into some more generic foundation, and from there you can again take it. And that works to some degree, and you could replicate that in the design space. All you have to do is now replicate the type structure for that thing, provide the transformations as services, and you can do that. Or an alternative is you can actually choose to say, there is no generic representation. It's possible. You know, we like to think that anything can be generalized, but some things probably don't quite fit as nicely together as we'd like to think of them. In this case, other mechanisms aren't necessary. In the most extreme case, using the repair mechanisms I mentioned, using consistency checking, at least becoming aware of it.
And another follow-up question in this direction. To establish the links, like one approach that could be potentially used for this is, if you think about the scenarios, like similar to what we do with behavior-driven development, and you think about the test scenarios and also the security hazards, the potential ones, and then you think about the potential causes and try to link them to the hardware elements or to what could go wrong where, to link the requirements to the hardware components within your cyber-physical system. Does your approach also cover the way how to identify the traces, like how to know which requirements will exactly link to which component of the cyber-physical system? How do you identify them? Is it part of the approach also?
The design space really is more like an open-ended question in that regard. I think this is an environment where you can try to explore exactly that, because it provides you with all the information. We have not investigated all sorts of traceability choices. Like the thesis that I mentioned beforehand was about requirements in code. So we focused primarily on that. But traceability between some component structure and some other diagrams may require other mechanisms. And no, we have not investigated that. In fact, there are lots of possibilities of what one can do there. And this is another avenue where I think if someone is interested in doing this, then the design space can provide an engineering foundation to exactly somebody else's thesis to explore that more interesting subject. And that's how I really see people working with the design space as, you know, let me get rid of the basic problem of how to get my data represented. Let me focus on the actual content that I want to focus on. And a lot of my PhD students are doing exactly that, focusing on content. But there is so much that still needs to be done. But here we also, at least I believe, we also have this very cool effect that there are very few people who have an environment where they can start exploring this. And this is where to work with the design space comes in. I hope I was able to roughly answer this, but
I have one more, but other people.
Thank you for your talk. It's an interesting topic. And my questions, firstly, I have so many ideas and questions about this topic, but I will limit it to two questions. On the GitHub context, I think when the GitHub understands the code change in the future, the toolkit can guide the developers to improve the code review. For example, GitHub can indicate the developers when a method was added or refactoring type was applied, indicated from a tag or anywhere. I think that it could be possible if these tools combine information like committee messages or pull request messages and pull text action. My question is about, do you know some work or related work that can combine this information? Do you know some working about that?
You touched on a bunch of different things, so I try to make sure I try to cover. You mentioned, I think, that the commit messages and the fact that you can actually extract information from them. You're right. There are tools like refactoring miner that would try to extract meaningful information, and that is what useful. But to me, this is the wrong thinking process, because this is after the fact that we didn't properly version control the data. We're still trying to understand what happened to the code. If we had done commits differently in a change tracking manner, where we actually understand what the changes were rather than what the differences are, we wouldn't need refactoring miner. That tool would be entirely unnecessary by just rethinking how we commit information, how we propagate information to a place like a GitHub. So this is a tool that solves a problem that shouldn't be a problem. But for as long as it's a problem, it's a fantastic tool, right? So that's what about GitHub. And that's why I think the design space we're thinking is the right way of thinking, but it doesn't invalidate GitHub in any way whatsoever. You can now encode all sorts of information with commits. So one of the things I didn't mention about the design space, it also has a version control mechanism. It also has commits, updates. I didn't show much of this for the same purpose, because it's useful. And what you were saying beforehand, that you can annotate information, you can add information to it that explains things, yes. And that is useful. It's being used in engineering, and there are lots of papers that demonstrate that there's a benefit in doing this. I think that's the premise. I think there was a third part to your question that I forgot.
Yeah, maybe about the work that investigating how to combine information from PUC-Rio to indicate developers about the code change. For example, in this committee, we have addition of the method, refactoring type to guide the developers to improve the code review. For example.
So basically, you're trying to ask me about how else we could combine information, or which platforms exist to combine information like that.
Yeah.
I think that there's a lot of environments out there that try to, in some ways, combine. I mean, you mentioned beforehand, Stefan Biffel's work with automation. Now, that's one way of moving information one place to another one. GitHub is another way of doing this. You have these platforms like Microsoft Azure or IBM Jazz. But all of those have certain limitations. For example, if you take Microsoft Azure, there is an assumption that you don't really understand what the change means. It simply represents what you did. You can modify an engineering artifact, and it's modified. If you look at it, after it's modified, you see the new state. If you look at it before modification, you see the old state. So it doesn't really foster collaboration. It doesn't really foster the understanding of change. And in that sense, a lot of existing technologies do a little bit of the design space. And we always felt like there was nothing there that actually provided the comprehensive set of things that we cared about. So at the end, we didn't find anything that really gets the information together we want to, but it may well exist, I suppose. I just haven't been very good at finding it.
Thank you.
Yes.
Alexander, thank you for your presentation. I really enjoyed the motivating examples of physical systems. I'm currently investigating the social technical aspects surrounding the collaboration of development teams with such a diversity of profiles and backgrounds. And one of the key issues that we are looking, it's about how to assure the traceability. You told me about that traceability between the software and not necessarily software artifacts, maybe hardware artifacts. I would like to listen your opinion about the role of inspection practices, inspection techniques to support this daily decision making of the team.
There are a lot of activities that we've learned over the last decades that are useful. Inspection is one of those activities. I see in context of the design space no difference whatsoever. You would be applying, you would be able to use it more or less the same way. What the design space would allow you in a more live way interact with that knowledge. It makes it more available, I suppose, to people. But at the end of the day, I think inspection is a wonderful tool to do exactly what it's supposed to be doing. We're not trying to reinvent the wheel necessarily, but sometimes we discover that when we try to apply things to the design space, that sometimes we have to maybe adapt things a little bit to make it fit this context. For example, a lot of technologies exist on how to provide feedback to engineers, and a lot of that, interestingly enough, is not change driven. If I do consistency checking, let's take the simple example of consistency. I'm having an easy time with that and inspection, but it might be true for there as well. And you have a large amount of data and you want to check this, it costs a certain amount of effort and time to do this. Then you get a result. If you don't remember that check and 5 seconds later you get a change in there, are you going to rerun the whole consistency check of this all amount of information and generate again all the error messages that somebody just went through maybe and acknowledging or not? This doesn't work. So somebody coming up with a smart way of consistency checking in terms of what the rules are and how meaningful they are is incredibly valuable for the design space. A mechanism that is not incremental is maybe not useful, but maybe isn't quite useful for that purpose altogether, because then, at the end, I believe that any mechanism that you work with needs to be able to understand progression of time. Whether I already provide that information. So if I make a change, do I really want to, what I want to do is want to analyze the impact of that change onto the overall consistency, which in fact is not a PhD thesis, exactly what we're doing about, incremental change tracking. But that's already like a long time ago, where we can do very effective consistency checking because we always focus on the change. And this is perhaps the part where I find the biggest differences when we think in the design space context versus a lot of state of the art, that we always have to rethink what it means in a change-driven world. And the very basic foundation of the design space is change. Everything is about very basic definitions of changes we have defined. So basic operations, change operations, and in that sense, inspection would have to be investigated too. I hope that makes sense.
Yeah, that's true. And one more question. Are you also investigating, for instance, how this background that people from engineering bring for the project, how their expectations, their needs, their motivation, or how do you see that?
This is incredibly hard. I mean, this is exciting. I wish I'm more of a social people who understand or try to analyze social behaviors of people and teams. I'm not. I'm a computer scientist. So there is a lot of interesting part about how teams function and what teamwork means to do. And I'm trying to read up on this, but to be honest, this is very exciting in many ways and something that is the foundation here. What I'm least excited about by environments like GitHub or version control system is that it's I make a change, I commit it, you can then update and you can modify what I did, you can then commit it. And when we both do a change, then we have a conflict and then we have to go through conflict resolution. It doesn't feel like this is really teamwork. It feels a bit like, yeah, it works that way, but it feels awkward. So I'm always wondering how it can be done better. And this is one of the nice things. I'm not the only one working on this. There are tons of papers of people out there who are re-envisioning what teamwork means, also from a social, but also from a technological aspect. Who needs to see what information when? When do I need to provide information? How quickly should I provide information? Even to the point, is it meaningful to provide instant feedback? Sometimes not even that is necessarily true. The design space can provide instant feedback, but you know, it doesn't have to if you don't want it, for example. But if you do want it, it's good that it can, right? And this social aspect, if someone ever wants to study this more, it would be exciting to work with them. Absolutely.
I would be social technical.
Yes,
There's some understanding that these things are indicated there.
right. No, it's a fascinating area.
Thank you much for your very interesting and important talk. Actually, I'm starting to coordinate 2 labs, one hardware lab and my own software lab in the area of IoT. So I think they can use your design space. But how do you compare with this design space approach, which is kind of automatic tracing of change, with some kind of guidelines that you give to the engineers? So if you detect something to change here, then you have to post this to the other guy because you know that his part is using your. I mean, this design space seems like you define the traces, and whenever something happens in one model or in one representation, then the other guys that are working on the other artifacts get notified. But is this effective or not? I mean,
Let's come back to the social.
yes.
Yeah, but the question of yours is an excellent question. It has so many implications. One part is who needs to know what. Part of the design space is that people can work separately. So when someone changes something and it causes an inconsistency, they can isolate their work well enough that they don't have to bother other people. So there's a multi-stage commit update mechanism where people working in a team can choose, one team can choose to ignore another team, or team can actually choose to work together with another team and see each other's changes. This is one of the many settings things that I didn't talk about, but you kind of get the idea from some of the demos where you can see this, tools get updated live. And if you have the ability of live propagating changes from one tool to another one, you also have the ability of not propagating right away, delaying propagation. And this is where a lot of the excitement is, because what you said correctly is there is no right answer. It could be this way, it could be the other way. And in some cases, it may even be that there never is one answer. It could well be that, imagine your own work. Sometimes your door is open because you're okay with being interrupted. In some cases, you close the door because right now I don't want to be interrupted. Imagine for your engineering work. I'm changing a part of the UML. I'm trying to update the code. Please don't do anything with my code while I'm doing this. Right? In other cases, you might be waiting. Okay, now I have time to look for stuff. Can you just push forward me that information? So the design space provides you the hammer, the mechanism to move the information around any way you want to, more or less at any time you want to. And now our question is, but should we, and what rules should there exist, in what ways it makes sense? And this is exactly the excitement for the design space, because now you can play around with exactly these situations. What would be an ideal process? And would that really lead to an improvement? And, working with industries, I think that was the second question. One of the reasons we like to work with companies is because then at least we can start asking questions like that, because it's kind of hard to figure out. I mentioned Bosch earlier. So we have the pleasure of working with Bosch on a project where we do process guidance. So we're not just representing the system knowledge, but we're also representing the engineering process in the design space. For example, that if you do something and you commit something, and but a part of that hasn't been approved yet, then the commit shouldn't succeed. They have very stringent rules about when and how something can be propagated, when something can be approved. If you try to push something to another person and certain checkboxes haven't been approved, then maybe that shouldn't be happening. So they have these control mechanisms in place, not for the system, but for the engineers. And these process guidances are now being used as part of the design space to monitor whether the person is allowed to do this at this stage, or whether it leads to an inconsistent engineering process. This is yet another thing. In the design space, has no notion of what the data is. You can represent any kind of data. You can represent process data, tool data, variability data, right? Whatever it is that you want to represent with it. And in that sense, my answer is a bit disappointing because I have to basically tell you, we haven't done much of this. You can do it yourself, so to speak, when we can provide assistance and we can actually work with you on this. But to me, this is exactly why we created the science.
And there's also the problem of the meta change, in the sense that the tools that we are using, we also evolve with the time.
Yes.
So we have already implemented all the traces between the tools that are not that you all like.
Absolutely.
Have to retrace all the things again.
Wesley is smiling. He's writing right now a proposal with some colleagues in France where we talk about meta-model coevolution. You know, Java, my code is in Java 8, and now I have to change some of this code to Java 16. But only some of the code, some of the other code shouldn't be changed. So now I have coexistence of two different.
It's a mess.
It's a mess, but it's reality. And coevolution is another part that I find an extremely exciting project. So, you know, I'm looking at Wesley again to get the proposal done, so we can get some funding for it and high resistance.
I have another question. I'm also from distributed systems, and it's much harder because when your system works, if all parts work, correct collaboration. So, and what you showed here is more like the design of one robot, one artifact.
Yes.
But if you have to think about the context in which the multi-robot systems work, you have to check if the evolution of the multi-robot system is compliant or consistent with the new situation in which you want to use the multi-robot system.
Then this is yet more information that you somehow have to consider in the engineering process, and you have to find out how to represent that knowledge. And if in some ways interacts with the engineering process, then you would want to model and describe that. Yet another example that basically shows that nothing that the science base provides takes you away from all that thinking work. Right? It doesn't give you any of the answers that you're asking. It's a wonderful example to say, but it provides you with a mechanism to at least start exploring the answer. So it comes down to all the examples that you give are beautiful examples of why the science base is just a beginning. And nothing I showed today is a meaningful end-to-end thing. Yes?
Hi, my name is Lisa. Thank you so much for your presentation. It was really good. I'm not actually an undergraduate for computer science, but I loved it so much. Thank you again for coming. You said that the design space of product is more of a research space that you can add on and create more tools to help on this process. So I was curious if there's something that you and your team are working right now as a new feature or as a new tool to help this process, or is there something more exciting that you want to work to add onto this space right now that you can share with us?
Well, I guess there are two ways of answering that. Number one is how can people work with the design space? So anyone who wants to work with the design space, what we usually do is we make them available the code. We give them the way to give them some ways of interacting with people at my institute so they can get question answers kind of going. We are not a company, so we do it ourselves, but this is something we'd like to do. And this is how you mentioned you're an undergrad student, right?
Yeah.
If you want to do a bachelor thesis and you're thinking of a topic where the science base can be helpful, write us an email. Maybe it works out, but we can send you this, and maybe you can actually use it for exactly that purpose. So that part is relatively informal. And so the second part, what is it that we actually want to work on? Well, this is the funny thing. We want to work on things that people are excited about. So if you have an exciting topic, for example, I mentioned this best paper where we just started models with automatically propagating values, just the same value being propagated around. It was a master thesis from a student. And we were like, oh, this is something that we wouldn't have done if that master student wouldn't have shown up at that time, and we just happened by random chance an interaction with a company where they had a problem that looked like that. So we did that. This is exactly the kinds I call it low-hanging fruits that we're looking for, because there's so many ways in how we explore this that I'm most interested in finding out what people can envision as a future in a world where engineering knowledge becomes more integrated. And I think that's really the key point here is, how do you integrate engineering knowledge? How do you share that integrated knowledge? Who and in what ways can that information can be modified? In what ways are other people bothered or not bothered by modifying the shared engineering model? How you deal with all this variability now of that engineering knowledge? And there are so many questions there that all of them are exciting. And I cannot know, I only have so many people, but I'm very excited to talk to anyone who wants to pursue this in some ways. The areas that we will definitely explore a lot in the near future is really about guidance, process guidance, the one I mentioned beforehand, trying to help engineers along the way, because most process modeling tools don't understand what the engineer is really doing. They say, you should be doing this, then you should be doing that, but it doesn't know whether they actually did this or that. And the other thing is, commit only when you're done working through a document or something like that. Have to work through a document, right? By using something like a design space, you have more information to work with, where you can actually provide process guidance a bit more meaningfully. So this is very exciting. Co-evolution, you mentioned that, is another exciting area. And we have a range of PhD topics around the design space. Variability, yes. Variability, we have a proposal on the submission right now where we want to do what I mentioned beforehand when I mentioned this, taking a feature out of a system, and the feature is now attached to all sorts of tool knowledge, and plugging that somewhere else in. I think it's incredibly exciting, because this has to do with reuse. And lots of you are probably familiar with reusing code and how hard it is. And now we're talking about reusing models, and not just doing them separately, but reusing them concurrently in some ways. So they are in sync as part of their reuse. And this is just a whole new dimension of reuse complexity right there. Exciting. All right.
Questions?
I have one last question. It's about the print screen. I think IntelliJ print screen.
Which one?
Print screen that IntelliJ.
IntelliJ.
Yeah.
I guess I have IntelliJ.
The requirements, the one with
Yeah.
IntelliJ requirements.
This one here, right?
Yeah, but the before with the highlighting green.
Ah, that one. It was here.
Yeah, yes.
Yeah.
Let me see if you understand it. This is a plugin of IntelliJ, this part highlighting green and red.
So what happened is, okay, it's covered here. Basically, as people use these tools, so requirements tool, IntelliJ, that information is in the design space. And then we showed the example that that information is now added with traceability. So I have my requirements traced to the code. And then it happens in this particular case that you have, for example, a method or a class, I think that's a class, that is not related to any requirement. This is a very trivial example. There are 3 requirements here, and this class doesn't have any relationship to any of those requirements. Okay? So it simply is some code, and nobody knows why it's there. There's no requirement justifying its existence. And that example was simply a way of saying you can even detect that now automatically. It's a trivial example, of course, for the sake of demonstration, where you can tell you if you've really forgotten something. So imagine if you come back to the GitHub example and I'm committing my class now. Let's say I made a change to the point class, that's what it's called. And now I'm trying to commit it. Wouldn't it be nice if someone said, oh, by the way, you forgot to trace that to any requirements, because right now it's not traced to requirement. maybe if you want to think about to which requirement is supposed to be traced, so you can provide this kind of guidance, among other things.
Yeah, because this picture, I have an idea from this picture. For example, in that they can provide in the picture information to increase the traceability. For example, the developer make a Git pull, update the code, and the IntelliJ can provide this method was added from the committee, and this method was added because this feature is and the feature plugin can provide this information. Because currently the developer needed to visit each class to understand what the change was made in each class.
Right. We can talk about it. Possibly it could be relevant in this case.
So let's thank again Alexander. We had almost 20 people joining via YouTube, so in total we had 45 people joining. So thanks again for the nice talk. I think it's a huge success because, as you know, we are here in the summer break. So for some people, the Brazilian academic year starting this carnival. So it's a very popular talk.
That's a good tradition. I can see why.
So thank you.
Thank you for listening. I really enjoyed the talk. Thanks for the many good questions.
Thank you.